Coming to you from Haleakala on Maui. In this screencast, we're going to look at random graph models. Specifically, we're going to have some examples of fitting the GNM random graph model, configuration model, and degree-preserving randomization to a natural network. This screencast assumes that you are familiar with basics of R and igraph and have studied the basics of these models. Okay, here we are in R, and I'm going to load the igraph library. For this example, I'm going to use this Yeast Protein-Protein network that you can get via the SAND library by just saying data yeast, but I've saved it to a file, which I'll load in. It's a GraphML file. Print out the network here first by typing yeast to the metadata. It has 2,617 nodes, 11,000 edges. And notice here that there are some attributes that are attributes of the graph. That's what the G means. This tells us where the information came from, the author, the citation, the URL. And I'll just show you the GML really quickly. It shows up here. You can get the actual citation for the data and read more about the data if you're interested in it. Okay, so let's move on to the analysis here. First of all, we're going to look at random graphs. We can generate random graphs given the number of vertices and the probability of edges forming between pairs of vertices. But in our case, we're going to use the number of edges since we know the number of edges. And we just saw here that we've got this number of vertices and edges. So we're going to sample from GNM. We're taking a sample out of the space of all possible graphs that have this number of vertices and this number of edges. And if we take a look at it here, it will have the same number of edges and vertices as the original graph, but it's an Erdős-Renyi graph, which is going to have different connectivity. Now, in a previous screencast, I showed you how random graphs grow, and there's these regimes of subcritical, critical, supercritical, and connected, and we can predict where it should be by looking at the degree, the mean degree of the graph, which, by the way, should be the same as the mean degree of the random graph. Maybe I should have had that in here. Let's throw that in here. Yeast.random. Okay. And compare that to the log of the number of vertices. This is the natural log. Since the mean degree is larger than the log, we expect the graph to be connected, or at least very, very close to connected. So the original graph is not connected, so that means that the random graph model is missing something about the original graph. We'll see more about that in a bit. The random graph I constructed is connected. Well, let's look at the component distribution here. So we're going to decompose the original graph into its components, and we're going to count the number of items in each component. So we got a giant component, one of them with this many vertices, and then this distribution, for example, there's 63 components with only 2 vertices, whereas our random graph, all of them are in one component. Okay, so we see here that the random graph fits the prediction that since the average degree is greater than the log of the number of vertices, we expect it to be fully connected, and it is. The fact that the natural graph is not fully connected suggests that there's something different about the random graph, although I wonder if it just means that we haven't done enough research to fill in all the relationships between the proteins. Interesting question. But let's look at some other things. Distances. Diameter of the yeast, the natural graph is 15. Diameter random is about half. Similar for average distance. So they're not the same. That's not a huge discrepancy. It's not way off, but they're not the same. Now, transitivity is a different question. Random graphs always have much, much lower transitivity than natural ones. So here's a natural. The transitivity of the yeast graph is 4.6. Of the random graph is 0.003, so about 100 orders too low. And this also holds if we, instead of using the global transitivity, the average of the local transitivity, we're about 100 times too low. So let's look at degree distributions. We're going to build up a plot here comparing different models. Okay, so I'm going to go ahead and make a probably way too large image here. Let's see, let's get everything back here. Okay, so we're going to divide it up into 4 regions, and we're going to first plot the degree distribution of the original graph, and then we're going to plot the degree distribution of the random graph, and take a look. And you can see this is classic. Natural networks tend to have this power law distribution, and random graphs have this normal distribution, which doesn't match at all. So that's one of the things we're going to look at here. Okay, we're going to write that out to Gephi. This is the expression you use to do it. Actually, I've already done it, and I've already loaded it into Gephi, so I won't do that again, because I'm saving time by having it already in Gephi. In fact, here it is. I have run Force Atlas 2 on it with some in linlog mode. I colored the nodes by some data that's internal to the yeast. There's classes of proteins, and I have sized the nodes by their average degree. So you can see there's definite clustering of nodes, and there's some smaller isolated components that we saw in the table of component sizes. So let's compare. We'll compare this structure to what we get with a random graph. Well, the random graph, when we graph it, notice the degree distribution is more uniform. Remember that random graphs' degree distribution is tightly clustered around the mean, so a lot of them are just all the same degree. And also the connectivity, there's no real clustering. I can't discover any structure in here. That's of course the meaning of a random graph. Okay, we've just seen that the random graph doesn't handle degree sequence. It doesn't give us the same degree distribution at all, and that's what the configuration model is going to fix in a hacky sort of way. It just forces the random graph to have the same degree distribution. So let's take a look at that. Okay, we're back here in R, and we're going to get the degree sequence of the yeast graft. I'm not going to print this out because it's really big. But we need to, the configuration model, we tell it what the degree sequence should be, and it'll generate it respecting that constraint. Read this documentation to understand the method we're using here, sample degree seq. We're giving it the degree sequence, and there's 3 methods. The VL is the most sophisticated. I've encountered some graphs, including some that I assigned in this class, where it hits an error in igraph and you can't use it, and then you have to use one of the other methods. So experiment to see which one fits the best, but fortunately this one works. And so you can see if you compare our graph to the one we've generated, we've got the same number of vertices, same number of edges, but now it's a degree sequence random graph. Now the VL method is supposed to make a simple graph. If you use one of the other ones, you may have loops and or multi-edges. This one's simple. We're going to throw this into the plot just to convince ourselves that the degree sequence is the same. And okay, I've made the window smaller so you can see it all. Let's now get back to looking at other aspects of this distribution. So we're going to predict that because this is a random graph, we're going to have a giant component. So yes, it's connected. So again, the original graph has this component structure, but our random graph constrained to the degree sequence, like the other random graph, has one giant component because it's in the connected regime predicted by Barbasi. Okay, let's look at distances. The original has 10. Again, these are about half as much as the original. Not way off, but not a perfect fit. Now let's look at transitivity. So what we see is the original graph has, again, a very high transitivity. Our last model, the random model, was 100 orders too low. But the current model, constrained to the degree sequence, is only 10 times too low. So this is kind of interesting because it tells us that some of the transitivity can be accounted for by degree distribution. That if we constrain the degree distribution to be a certain way, it's going to force it, even though it's random, to have enough clustering to get 10 times higher. But we're still 10 times too low. And this also holds when we look at the local average. So that's 100 times too low. This one's about 10 times too low. Okay, again, we wrote this out in the Gephi, and let's go to Gephi to see what I did on a previous pass of this. So here's the configuration model constrained to have the same degree sequence. So notice that the connectivity is still random. There's no real structure here, like this one has no real structure. But the nodes are sized by degree, and now we see the expected distribution like we had over here. There's a few high degree nodes and a whole lot of low degree nodes, just like there are here, because the the degrees of the nodes are exactly the same, at least in terms of the distribution, but the connectivity is entirely different, which is what gave us issues with the transitivity and maybe also with the distances not being quite right. Next, we're going to look at degree-preserving randomization. This model here, degree-preserving randomization, makes sure that each vertex preserves its degree, and we're going to see in a bit also an advantage of this is it works on the original graph, so all the attributes of the nodes of the original graph are still preserved when we look at it in Gephi. But what it does is it picks a pair of edges and it just swaps their endpoints. So the source of the two edges, those vertices, retain exactly the same degree sequence, and you can read about it by executing these two help queries. So we're going to use this rewire method. We're going to rewire the graph with the constraint of keeping the degree sequence, and we're going to do it enough times to make it really random. I'm going to do it 10 times the number of vertices, and this will take a little while. If your computer is slow, you should maybe drop that number down a bit or go make a sandwich. Okay, it's finished. Again, we know the degree sequence is going to be identical. We'll just verify it by graphing it again. It's identical. Let's see whether we've gained anything over our previous model in terms of modeling the connectivity. There's the original graph. There's the previous degree sequence model, and here's the rewired model. Well, not much different. It's got a few more isolated components. What about distances? The original, the configuration model, not really different. These are not different, so we don't really gain anything there either. Transitivity, here's the global transitivity of the original. Here it is 10 times too low, the degree sequence, and the rewired one just slightly higher, but really not different at all. So again here, just slightly higher, but not really much at all. So it's basically the same model. It's not giving us a whole lot more, although one advantage of it, if we go to Gephi, and here I've read it in, the rewired one, it preserved I'm going to the data laboratory here, it preserved all the attributes on the nodes because it's rewiring the original graph and it's keeping the same nodes. Whereas the random graph, it's just making new nodes. So here's the original, here's the rewired, it has the same attributes. So I'm able to do things like color it according to the class of the protein like I did in the other one. But here, so I do have the degree sequence gave me the right distribution of vertex sizes, just like I do in the original, right? But the connectivity is more like the random or the degree sequence. It's just kind of a fuzzy mess. So what this tells us is we are able to take care of degree sequence, but we're not so-so on the distances, but really bad in transitivity. And transitivity is exactly what the small world Watt-Strogatz model is supposed to take care of. And I'm going to put that in a different video just to keep this one from being too long. So that is the end of the video on random graph models other than Watt-Strogatz that will come next. Saying goodbye from a bluff high above Polyku cabin in Haleakala.